Okay, sorry for the wait, everybody. Okay, so if anyone's done genetic algorithms in university, we're going to have to cover some of the basics. So the first 20, 30, we're going to be covering what you may have already done at university. But then we're going to get onto some of the more advanced topics, some of the more research things, if we can get some time. So let's see how it goes. So first off, what are genetic algorithms? So genetic algorithms were invented to mimic the processes observed in natural selection. So many people, biologists included, are astonished that life at the level of complexity that it is could be produced by genetic processes. The idea that genetic algorithms use this power of evolution to solve optimization problems. So we're going to look into that. The father of the original genetic algorithm in the 1970s was John Holland. And he just basically created an algorithm from looking at the way how DNA and natural selection, Darwinism, worked. So, genetic algorithms are basically adaptive heuristic search algorithms. There's lots of other heuristic search algorithms out there, but these are based in the ideas of natural selection and genetics. As such, they represent an intelligent exploitation of random search used to solve optimization problems. Although randomized, GA's genetic algorithms are by no means random. Instead, they exploit historical information to direct the search into the region of better performance within the search space. The basic technique of genetic algorithms are designed to simulate the processes in natural systems necessary for evolution, especially those that follow the principles first laid down by Charles Darwin. And I actually went to university in Edinburgh, and I stayed, I think it was 3 rooms away from where Charles Darwin used to stay, but where he used to stay was now a museum. So since in nature, competition among individuals for scant resources result in the fittest individuals dominating over the weakest individuals. It's better than conventional AI. So why would we use genetic algorithms? Why would we consider looking at them, basically? So in a lot of AI models and statistic analyses, they're very brittle. So if you change any kind of problem encoding or definitions of the problem, you have to start again, or you have to really go back to the fundamentals and relook at your problem. But with genetic algorithms, they're a little bit more susceptible to change. They don't break easily, even if the inputs are changed, or the presence of noise. In searching large search spaces, multimodal state space, or n-dimensional surfaces, a genetic algorithm may offer significant benefits over a more typical search optimization techniques, such as, I don't know if you guys are aware of linear programming or heuristic, depth first, breadth first. There's also A*, there's many other algorithms for searching in a search space. But we're going to look at genetic algorithms today. And so let's look at what the algorithm for a genetic algorithm is. So genetic algorithms simulate the survival of the fittest among individuals over consecutive generations for solving a problem. So we're going to generate different populations of generations, and we're going to evaluate this for problems. So each generation consists of a population of character strings. Now, there may be character strings that we'll talk about encoding later on, but some kind of encoding, maybe ones and zeros, that we're going to call our DNA, that we're going to consider to be a potential candidate for our problem, solution for our problem. Each individual represents a point in the search space and a possible solution. So every chromosome would be a possible solution, and we'd evaluate those, how good those solutions are. The individuals in the population are then made to go through a process of evolution. So genetic algorithms basically are solutions. We're doing an analogy with genetics, and we're calling each solution a chromosome. Chromosomes, many chromosomes within a population of individuals. Individuals in a population compete for resources and mates. So how good we assess that individual solution to be, it dictates the likelihood of whether it will be able to make, and it will make it into the next generation. Those individuals most successful in each competition produce more offspring than those individuals that perform poorly. Just like in real life, I suppose, in humans, those that are more successful, get big houses, nice cars, do well in life, they're more likely to reproduce in the animal kingdom. Genes from good individuals propagate through the population so that two good parents will sometimes produce offspring that are better than either parent. So obviously if you combine the best of both worlds, sometimes you can produce something even better. Thus, each successive generation will become more suited to their environment, or so we would hope. Okay, so let's imagine a search space. So a lot of AI problems are basically a search landscape where this would dictate a large area of potential solutions. And within these potential solutions, there'd be many reasonably good ones. So you see many little peaks here. Now these may be suboptimal solutions, but much better than the surrounding solutions. And for example, here we have one solution which meets our goal in the middle here. However, searching that search space can be quite difficult, because if you're on one of these, you might have to go down in fitness before you can reach your final goal. So we're got to try and concentrate our search to find the optimal solution. Sometimes the optimal solution isn't required and we're happy with many of these solutions, but in this case we're going to say that we've got a large landscape and only one solution. So it's a difficult landscape to navigate for any kind of search algorithm.
What's that example?
So imagine we had a mathematical function where... Okay, so imagine we had a mathematical function. This would represent, imagine this was 0. Everything else would be a non-zero value. Our only solution would be 0. However, we might get very close to 0 at some of these peaks.
Right.
And then we might have to go away from 0 to a higher number before we can actually find our optimal solution.
But what would like a real-world application look like that would give that kind of result? Like a real-world application of genetic algorithms?
Involving, we're going to go through some solutions in a little while. So we're actually going to go through some solutions that have, I'm not sure if they have exactly the same landscape as this, but they have landscapes with lots of troughs and peaks and for, a few solutions.
So about SETI, trying to pick out stronger, more ordered signals amongst all the background noise. Well, yeah, because it's a frequency analysis problem, isn't it? So you've got a broad spectrum that they're receiving and you need to try and identify the candidate signals amongst that.
Yeah.
Why do you think SETI at home did all that distributed processing? It doesn't do an awful lot of number crunching. If you could optimise the algorithm they use and do more cycles, you get through more cycles per second, then you'd be ultimately more successful on a smaller resource base.
So a population of individuals is maintained within the search space for a genetic algorithm, each representing a possible solution to a given problem. Each individual is coded as a finite length vector of components or variables. So for example, we know we can encode anything in ones and zeros because we do it in computers. We just have to make a way of encoding our problem that fits the solution. To continue the genetic analogy, these individuals are likened to chromosomes. We've said that already, sorry. Thus, a solution, is composed of several genes. A fitness score, so for each candidate chromosome, we're going to assign a fitness score to representing the abilities of that individual to compete compared to other individuals. The individual with the optimal or generally near optimal fitness score is sought. The genetic algorithm aims to use selective breeding of the solutions to produce offspring better than their parents by combining the information from the chromosomes. Okay, like we said earlier with the diagram peaks and troughs, imagine that you were told to wear a blindfold and you're placed at the bottom of the hill with the instruction to find your way to the peak. your only option is to set off climbing the hill until you notice that you're no longer ascending anymore. At this point, you might decide, well, I'm no longer ascending, maybe I've found the peak of the hill, but how would you really know? In this situation, because you're blindfolded, you couldn't see if you're actually at a small peak or you're actually at the top of the mountain. We call this a local optimum. And this is a problem for genetic algorithms. And this is a problem we try and get past. So we need to escape from these local optimums if they're shallow enough. Genetic algorithms and many other search problems, it's not always the case that we have to guarantee one global optimal solution. There may be several acceptable solutions in the search space. And that's generally the case with more complex problems. Okay, so to represent that, we have our chromosome. We have a gene, so a gene would be one of the objects of the chromosome. So we made a list of objects. So let's go through the algorithm. The genetic algorithm maintains a population of n chromosomes, which are all potential solutions, with their associated fitness values. Parents are selected to mate on the basis of their fitness. Consecutively high fit solutions are given more opportunities to reproduce. As parents mate and produce offspring, room must be made for new arrivals, or the population is kept at a static state. Individuals in the population die and are replaced by new solutions, eventually creating a new generation once all mating opportunities in the old population have been exhausted. In this way, it is hoped that over successive generations, better solutions will thrive, while the least fit solutions will die out. So it's based on natural selection. So in the components of our algorithm are basically, we're going to generate an initial population of candidates. Then we're going to use selection over that population. We're going to look at crossover, which is basically when DNA in nature, DNA strands combine with each other, and what they do is they cross over and they have a point at which part of the DNA strand combines with the original. For example, if we have two chromosomes, chromosome A and chromosome B, chromosome A and chromosome B would combine, whereas part of chromosome A would be combined with chromosome B. The remaining part of chromosome B would be combined with the remaining part of chromosome A, and would have what's called a crossover.
So is what you're saying that when a mummy algorithm and a daddy algorithm love each other very much, they get certain urges?
And they create baby algorithms that basically are parts of each other.
Yeah.
And mutations, which are things like in nature, where you've got maybe you're living next to a nuclear power plant, or maybe there's little cosmic rays. Mutations can occur just as they do in nature, and that adds us diversity to our solutions. Without that, we may quite easily get stuck on troughs, remaining very static.
The more powerful factor, is it change through crossover, or is it change through mutation?
I would say it depends on the exact problem and the encoding that you're trying to solve.
So you can choose to make mutation more or less important factor.
Yes, exactly.
Surely if mutations still be a factor, you'll never converge to a real solution. You'll get closer because the two parents will meet and then you're just flying off the handle somewhere else.
Yeah, if you get too far.
If the mutation is too high, yes.
Yeah.
As is in nature, you would just have cancer, you go around.
Then technically mutation would also stale.
It would become stale and you wouldn't have new blood.
Eventually, yeah, it's
Well, that mutation would also stay.
Okay, so the first operation was a selection operation. And the key idea in the selection operation is to give preference to better individuals, allowing them to pass on their genes to the next generation. The goodness, I don't know why I said that, of each individual depends on its fitness. Fitness may be determined by an object, function, or by a subjective judgment. So basically, I've written quite a lot here, but when we look at a fitness function, we need it to be relatively performant, because we're going to be performing this fitness function many, many times when we're generating new populations. It doesn't always have to be For this reason, it doesn't always have to be exact. So maybe it's a large calculation you have to do to get the exact fitness. Maybe an approximation is good enough. And just for processing speed, it's maybe better to do that. But it is important to have a good fitness function that accurately gives a value to the utility of our individual in the population. So the next thing we can look at is crossover, which we just talked about. Two individuals are chosen from the population using a selection operator. A crossover site along, so if we're using ones and zeros as a bit string example, a crossover site will be chosen. The values of the two strings are then exchanged along this point. So obviously if we've got a string with all zeros, a string with all ones, and the crossover point is 2, we would have 1 1 0 0 0 0 and 0 0 1 1 1 1. The two new offspring created from this mating are put into the next generation of the population. By recombining portions of good individuals, we hope, anyway, the process is likely to create even better individuals. So that's a slightly different crossover than we're going to do, but you can see that it's basically crossed over at point 1 and 5, and then the recombined offspring is over here. Sure.
Just for a sense of scale, like how many bits would a typical solution use in a chromosome?
It really depends on the problem.
But like, would it be like 1,000 or 10,000, or would it be 100, or like what kind of scale are we talking about?
Typically, you can solve quite complex problems. I mean, if you're in a search space, for example, that was 2 to the power of 1,000, like you say, it would be a large search space. Unless it had quite a few solutions in there, you know, it'd be a hard search space to search, obviously, given just computationally. So generally, these problems are in a smaller search space, maybe 10 to 100, typically.
Okay.
But it depends on the solution. And also, there's what we'll get onto in a minute is chromosomes. There's another point where chromosomes can actually grow. You can make chromosomes that can get larger. Okay, so mutation. With some probability, a proportion of the new individuals will have some kind of, so in this example, it'd be their bits flipped, where you've got more traditional DNA with not ones and zeros, but maybe 5 different values. You have different mutation options, so you could just pick from the dictionary and swap a single bit. You may also have restrictions such as you have a solution where you must use 5 letters, so you must have A, B, C, D, E, but you can recombine the combination. So in that case, you'd want a mutation operation that maybe did a swap rather than just did a simple mutation. We'll look at that in a minute. Mutation induces the random walk through the search space. So mutation adds that random element to where we're going to head next into the search space. Mutation and selection without crossover create parallel noise-tolerant hill climbing algorithm. So without crossover, if you just did mutation and selection, you'd have a noise-tolerant hill climbing algorithm, basically. So we're looking at mutation. He's mutated 4 bits, sorry. Using selection alone, we'll tend to fill the population with copies of the best individual from the population. So selection alone, certain individuals will dominate because they're the best individuals generally. Using selection and crossover operations will tend to cause the algorithms to converge on good but suboptimal solutions. Using mutation alone induces random walk through the search space. Using selection and mutation creates parallel noise-tolerant hill climbing. So let's go through the basic algorithm. So the very basic algorithm from the 1970s was first of all, we would have a population size. So say it was 10. We would generate 10 random, given the rules of our problem, we would generate 10 candidates. We would then apply our fitness function to each of these 10 candidates. And then we would go into a loop where we select the parents based on a random element plus so we would base the selection of the parents on a randomly generated element, but it would be in proportion to the fitness of the individual divided by the fitness of the entire population. We would then perform crossover, we would then perform a mutation, and we would then perform another fitness calculation on the population. And basically we just repeat that until we got a solution that we thought, right, that's good enough, that meets our goals. So I've got it written down here as a diagram. We can see the selection comes in, we generate the first population, we then evaluate it with the selection function. There's different selection functions we could use here, but the most common is what's called a roulette wheel, which basically you would just assign a proportion of probability to the fitness, so that individual's fitness divided by the total. You would then do a random spin, you would land somewhere, but the likelihood is, given the size taken up by the fit individuals, it would control the probability that you'd likely land in a fit individual. Once we'd chosen some candidates via selection, via roulette wheel, we'd then do crossover, mutation. Then we'd say, do we have a candidate that's good enough? If not, we'd go back and do all that again. If yes, we'd pick our best and print out, display our best solution, or our winning solution. So we're going to quickly look at that. I would implement that in C# quickly, C#. Specific to each problem. So first thing, let's have a little look at the code quickly. Let's break it up into components. So the first thing we've got here is a genome. Sorry, a genome. I should have called this chromosome. In fact, this is my mistake. Whenever you see genome, think chromosome. I could have altered this quickly.
Well, why don't you just go, we've had to rename.
I would do, but if I do that now, I'm going to run into all kinds of problems.
Sure.
So on our chromosome, which we call a genome, we're basically saying we have a function to set random values. That's going to be used when we generate the population. So that's basically just going to go through our allowed values. I should probably mention, actually, first of all, what is problem specific? So in any given problem, our encoding of the gene of the chromosome is problem specific. We're going to decide that based on the problem criteria. The allowed values are also problem specific. We're going to decide what allowed values are given our problem. And our fitness function is obviously problem specific. So we're going to evaluate each candidate given the problem. Different problems would obviously have different functions.
We're filling the machine, we need to sit down. It's really more comfortable.
So that's the problem. We've tried to build an engine here where we can solve different genetic algorithm problems. A lot of, if you look at the examples on the internet of C# genetic algorithm, you get a lot of specific problem solving, which are very tailored to the exact problem. We've tried to be a bit more generic here and plug in a few different problems to the same engine. So for that, we've used generics just because you may want to change type depending on the type of encoding in the genome. So for example, I may want to use integers, I may want to use Boolean, I may want to use objects. So first of all, the first thing we're going to do, if we go into the program, we're going to have a look at our genetic algorithm engine, which has a population. So the main function in our genetic algorithm engine to generate the initial population is here. That's just going to go around each member of the population and set random values from the function that we just looked at in our chromosome. And that's just going to set random values given the allowable values in our dictionary. Some problems you may obviously have other constraints, but the first problem we're going to look at doesn't. Second function we're going to have is, so once we've generated that new, that initial population, the next thing we can do is generate our next generation. So in here, we're going to go around each member of the population, and we're going to spin roulette wheel, which is that pie chart that we showed you earlier. And basically what that's going to do is it's going to go around each member of the population. And given the percentage of that population, of the total fitness, of that individual's fitness, sorry, divided by the total fitness, we're going to get a percentage. And we're going to pick those, we're going to generate a random number. And basically, if that random number, from 1 to 100, if that random number is less than or equal to a percentage, we're going to choose that chromosome. So if we go back to our generate next generation, we've spun the roulette wheel, we've got a new population, and we've returned that population. We have a mutation operator. If we go to that. Now, one thing to note here was when I was building this, I realized that actually I needed different mutations and different crossovers for different problems. So what we've done here is we've made an interface for mutation, which basically says mutate. And we're passing in a mutation chance. So in our algorithm, we're also going to define what is the chance of mutation. That's a variable we want to control and play with. So if, like we said earlier, a high mutation may result in a lot of problems, a too low mutation may result in a stale population. We've also got a crossover, which has a crossover chance. So we're also saying, what is the chance of any two genes crossing over? Typically, that would be higher than the mutation chance because it happens naturally in evolution with a relatively high frequency. Okay, so let's go back to our genetic algorithm engine. So we're going to do a mutation, we're going to do a crossover, and then we're going to generate the next generation, which is going to use the roulette wheel. And that is going to happen in a loop. So let's look at a problem to apply our genetic algorithm engine to. So the first problem we're going to have a look at is minimizing a function. So if I go back here, okay, so we've got this function. We have 4 inputs, W, X, Y, Z. Of those 4 inputs, the allowable values are from 1 to 99. Chromosome length is 4. And we're going to use random mutation, which means we're just going to pick a gene in the chromosome and we're going to mutate it within the allowed values. So if we go to our program now, and we have a look at our problem. So we've said max input value 99, genome length 4, allowed values is an integer. So we're going to generate the allowed values here. And then, as I said, each problem has a specific fitness function to evaluate any solution for this given problem. So the fitness function we've written here is we're simply getting the values. So the initial problem we've got is we want to find values for W, X, Y, and Z that basically equal 30. So we're going to do the sum, and we're going to minus 30, and then we're going to take the absolute value and divide 1 by the absolute value. So in theory, if we got obviously larger numbers are going to be bad. It's going to produce a very low fitness score. Decimals are going to produce higher fitness scores. And if the value is 0, which means we found a solution because minus 30 is equal to 0, this is what we want, we're just going to return int max. And that's going to allow us to differentiate, basically. So let's have a trial run of that. Okay, so what we've got here is we've got a little runner, we've got population size we're setting to 15. So we have 15 individuals in every population. Crossover chance between any 2 individuals is going to be 50%. We're going to use, of our crossovers, we're going to use our basic crossover. We're going to say mutation chance for any one gene is 15%. sorry, for any one chromosome is 15%. Mutation is going to be of type random mutation. And problem, so we're specifying the problem is function minimize, which is the problem that we just looked at with W, X, Y, and Z. Okay, so what we've got here is a loop, which is just going to call next generation. We're going to give the generation we're on. We're going to print that out. We're going to print out each individual in the population. Then we're going to wait for a key. I'm going to comment that out in a little bit, but I just want to show you one run. And then we're going to break if we reach int max, which are in case our goal would be reached. So let's play that. It's just a little console application. Haven't formatted it very fancily, so we'll see. Give it a minute to run. Okay, so we have done, so if we scroll up, we have generated an initial population, we've done mutation, then we've done crossover. And we have produced, so there's our initial population of randomly produced solutions. We've done roulette wheel, mutation, and crossover, and we've produced this generation, which has actually a slightly lower fitness. So that we can press key and we can basically let that work itself out. But what we're going to do here is we're going to comment that line out that I have to press a key. I'm just going to let it run. Okay, let's let it run. Okay, so it's running and it's found a solution. Okay, so how many generations did we take to find a solution there? We take 437 generations of 15 chromosomes. And given the search space, I think is 100 times 100 times 100 times 100. About 8 zeros. Is that right?
10 zeros?
10 zeros?
Yeah.
So that looked like a relatively efficient search. Okay, so that was great. We're going to check out the second problem we're going to have a look at is card sorting. So we've got an example of a problem here where you have a deck of cards. Each card, you've got a deck of cards numbered 1 to 10 cards. You can take those cards into 2 piles. The first pile is a sum pile. All the cards in this pile get added up. So 1 plus 2 plus 3, whatever's in the pile. The other pile is the multiplication pile. All the cards in the second pile get multiplied. So let's have a look at that problem here. So the genome length we're saying is 10, so there's 10 cards. The value of this, so the fit criteria for this solution, sorry, I didn't mention that, is the first pile of cards we want to be as close to 36 as possible. So the sum pile we want to be close to 36. The multiplication file we want to be close to 360. So we want both these 2 piles, the first one to equal 36, the second one to equal 360. Our fitness function, we're then basically just going to calculate the error in each of these and divide it by the total, which is 360 or 36. And then we're going to take the combined error and add them together and make sure we have a positive value. We're going to use absolute value. Then if we have a 0, we're going to return int max again to represent we have a solution. Otherwise, we're going to say basically the smallest remainder from combined error is what we want, so we're going to divide it by 1. So let me just program that in. Problem. Card sort. Okay, so we're just going to run it with the same mutation, the same crossover, the same percentages as the previous example. let's see how that goes. So this might not be the same parameters we used for the previous solution may not fit this solution very perfectly. So it seems to be running through a large number of generations. Doesn't seem to have found any solution yet. Okay, so what our parameters that we just put in there do not seem to be easily finding a solution. So let's have a little play with them. First thing we could do is we could say, instead of using a random mutation, we could change our mutation to be a swap mutation. So that's going to swap two genes instead of randomly mutating them. And then we're going to change the population size to be, let's try a population size of 20. And let's run it again and see if we can find a solution. Unfortunately, genetic algorithms is a little bit random. When I ran this earlier, it worked perfectly, but you never know for sure. So we found a solution. So we're saying if we had put 1 in the sum pile, 0 in the multiplication, 2 in the multiplication, 3 in the sum, 4 in the sum, 5 in the sum, 6 in the sum, and the other way around, sorry. So yes, 1 in the multiplication, 2 in the sum, 3 in the multiplication, 4 in the multiplication, 5 in the multiplication, 6 in the multiplication, 7 in the sum, 8 in the sum, 9 in the sum, 10 in the sum, we would have got 36 and 360. If anyone wants to do that on the calculator, please feel free. I did it earlier, it seems, yeah, it works. Okay, so you can see that the operations we use do have an effect on the search Hamilton for time. Okay, so I had planned to go on and do a little bit more. However, we seem to be a little bit tight on time now, so I'm going to concentrate it. So let's just skip ahead, sorry. So I think we've basically shown you the essential ideas behind genetic algorithms. So let's have a look at some other theories. Extensions of this is you can have multiple islands of populations. You can have migration between the islands of populations. It allows for, it has been informally argued that having multiple subpopulations helps preserve genetic diversity, since islands can potentially follow a different search trajectory through the search space. Another thing we could mention is chromosomes can also grow. So for example, if we wanted to evolve a solution for our Mars rover, for example, imagine we wanted our Mars rover to cover every square, and there would be a penalty with covering a square twice or not covering a square. We don't know in advance how many commands it would take for our robot to go navigate through the whole square. So we may allow our chromosome to be a variable length so it can grow. It makes crossover a little more complicated, but... And we can also generate a tree-like representation, a mix of both linear chromosomes and trees, and there's various techniques here. Genetic algorithms, one of the main things they're used for is training neural nets. So I don't know if you guys know what a neural net looks like, but basically it's a bunch of inputs. We have network with weights on it, and then we have associated outputs with weights. And the difficulty here, so it's generally made to represent a similar pattern to the brain. We've got neurons and connections in between. The problem we have with neural nets is we don't know how to train them very well. So we can produce a neural net, complicated like a brain is. However, training that to be useful like a brain is a completely different problem, and it's much harder. I was actually newly employed by a company in Partnership in Liverpool Street. They were building a neural net as a component in their pensions engine. And they were looking at ways to train that. And they had already looked at genetic algorithms. Another idea to extend this and make it more powerful is genetic regulatory networks. In nature, certain genes work together. And basically, they can be proteins can bind to these genes and make it less likely that they're split up during crossover. And that allows us to add a small level of modularity to what we're producing in our genetic algorithm. In my thesis in university a long time ago was basically analog circuits. Now the problem with analog circuits is they're great, they're far more powerful. In theory, we could build analog computers that would outperform digital computers, but we don't have good engineering patterns and practices to actually build these systems, because they've become very complicated systems with minor interactions making a big difference. So the idea was maybe we can use genetic regulatory systems, genetic algorithms, to modularly evolve analog electronics, which would be very powerful if we could do it. We had some success at turning a light on based on some various sensors, and people are still pursuing these things today. Any questions and answers, guys? Question?
I got one. Do you know much about the relative benefits of using backpropagation as opposed to genetic algorithms for training a neural network?
Yes.
You got a slide about that, haven't you?
I've got a slide about that. So backpropagation it's generally more efficient for a standard neural network, but
Which one?
so backpropagation is generally more efficient for a simple standard neural network. However, with neural networks, there have been advances where you've got multi-dimensional neural networks. We have good training algorithms for those. We can train networks that are a mixture, a mixture of different connections. So basically backpropagation is a lot more restrictive in the types of neural networks you can train with it. And more complicated neural networks, we don't have great training algorithms for, so genetic algorithms is basically a reasonable candidate for doing that training.
I don't know if with the backpropagation you can get a local optimus instead with the genetic algorithm. You can eventually find a global solution, because with the gradient descent you can reduce. So yes, you can start in a local optimus.
Yeah, I mean, local optima are always a bit of a problem. But yes, you'd hope that the mutation, if you set your mutation high enough and your crossover to certain, you'd be able to get past those peaks or troughs.
Collection of P45 on
Any other questions, guys? All right. Thank you very much, Dan.
Thank you.